Thank you, Alison. I have actually slightly changed the title. I thought the Glasgow Observatory was quite broad. So what I thought we'd talk about is a few of the environmental monitoring data streams that we've actually had running for almost 5 years now at the Glasgow Observatory. For those of you who are not aware what the observatory actually is, it is an at-scale, 200 kilowatt scale, mine water geothermal and underground thermal energy storage research facility. It's located in the south of Glasgow in a beautiful park known as the Cunningar Loop. In terms of the geothermal infrastructure, we have two abstraction, two reinjection boreholes. They are fastened together with underground pipes into a heat centre, where there is a choice of heat exchanger, which then links into a heat pump chiller, which can allow us to put heat either into the mines or take it out. But although we've got some fantastic results on this sort of thermal side, I'm not going to talk about that today. Instead, I want to bring your attention to some of the environmental monitoring data streams. When the site was firstly instigated, we realised that one area of research that is really important is to how do we monitor how the schemes are working? How do we know what effects it's having to the surface and the subsurface? And equally, in fact, more important, what do we know about it from a risk mitigation? Are there certain data streams that can give us an indication that something may not actually be working as we would like it to? And so we have got 8 different streams. Unfortunately, I don't have time today to go through them, but I would ask you and urge you to go and look at the UK GEOS website for more information. I am, however, going to focus on 3 today. I'm going to talk about the seismic, then the INSAR, which we've heard about a little bit earlier from a different project, and then finally the soil gas. So the seismometers. So the seismometers are installed in a slightly different site. Hopefully you can see it on the map. It's called Site 10. It's about 1.5 kilometers away from the main facility. We drilled a borehole there, 199 meters depth. It's now filled with water, and installed into that are 5 of these seismometers. And you can see an example on this slide. They are on one string and they are separated by 40 meters. And they're GURAP seismometers, and they record continuously. The sensitivity of the tool is actually around, for each individual seismometer, is about 2. But when you get the 5 of them together, then it can actually come down to a much more sensitive tool, and we can actually detect things in around the order of 0.5. So what I wanted to show you were just very briefly some results, and just make a point that although we've got baseline data and it is recording continuously, there are also certain things that you can see that change. So there are diurnal patterns, there are weekly patterns. Now these seismometers here, this is taken from our live stream that we have. And it shows you the top 2 pictures are showing you the record from the seismometer at 40 meters, whereas the bottom 2 show you the seismometer, the deepest one, at 198 meters. You can immediately see that the shallower ones are much more noisy. That's because they're actually influenced quite heavily by the surface noise, and the deeper ones have got less noise. But even within that, you can start to see a pattern. There is more noise, going down the y-axis. You can start to see that that's time. And what you can see is that there are periods of time where it's much more noisy, and they actually coincide with the working day. So you can see that from about 9 o'clock in the morning through to about 5, 6 o'clock at night, there is significantly more noise than throughout the night. Probably not surprising because of it being in quite an industrial area. You can also see, though, that the Sunday is quieter than the Monday. And that's once again because it is a business area. It's by the police headquarters. So some of you may be looking at that and going, well, that's a little bit noisy, and how can you pick anything out? Well, obviously, this leads into the national network where it is able to be interpreted in more detail. And we were able to show that there has actually been an earthquake in the area. So not an earthquake, but more like a microseismic event. And the one that you could see there is very small. It was about a 0.5 earthquake. It was around 30 kilometers from the site, but you could detect it on all 5 of the seismometers. And that was the difference from kind of backing out some of the other baseline data that you've just seen. The summary that I'm giving, and I'm going to give one for each one of these data streams, is my own subjective views from working with it for the last 5 years. The seismometers are actually very reliable. The picture on the right, you can see 2019 to 2025. Blue indicates the periods when the seismometers have been working, and white is when there was no period of operation. And there was one area which you could see in 2022. This was when we did have a failure in one of the seismometers and it was removed from the borehole. But other than that, it's been a very, very reliable piece of equipment. There was a high capital outlay. There is a reasonable running cost in terms of power, but it's quite low in terms of maintenance. The data is taken, it's processed and interpreted. And we've been able to state that really the seismometers deeper than the 100 meters are less affected by the surface noise. And it is a very good risk mitigation in a way of being able to identify any key microseismic activities. Moving on to the INSAR, and I really thank the person earlier who provided the talk on INSAR, because I'm not going to go into the main technical detail. INSAR, as you know now, stands for Interferometric Synthetic Aperture Radar, and it uses satellite data to actually map the deformation or the variation in the ground level. We have on the sites themselves, on site 5, we have a passive reflector, as you can see in the picture. And on site 1, we have an active reflector, which actually just pings a signal up to the satellite and then it's returned. We use 3 different satellites, including the Sentinel-1 that was mentioned earlier. And again, this gives a continuous acquisition and it feeds into the national network. So we use a calibrated product. It's provided to us annually. I'm not going to go into great detail. Suffice to say that any of the colours that you can see on the maps in the other area is that green is showing that there's been very, very little movement. So our baseline data set was done prior to construction. And since then, we get this annual update, green showing minimal movement, red and blue are showing movements in excess of 3 millimeters, so still quite small. We've also got the results shown in much more of a time series. This is the ascending and the descending, and that is showing that the average kind of variation we're getting is plus or minus 1.5 millimeters. So we don't have to, at this point, be concerned about any changes in the ground level or any subsidence. The summary, it is reliable. It was low capital outlay, very low cost to run. The data is processed and interpreted for free as part of the national network, and it will identify any changes. At the moment, the downside to this is that we get the results annually. So it can show the start of something, so we will be able to pick up a future issue. It can show something perhaps that happened in the past, but it's not really able to provide information about any live event. So we may miss something if it happens in that immediate time. The final one I want to talk to you about is gas clams. You can see a picture of a typical gas clam. They're about 1 meter long probe. We've put them directly into the soil. Quite often, these are deployed into boreholes and they're used to measure gas sort of volumes that you get within the boreholes when you open up the chamber. But these ones are going directly into the ground. They measure every couple of hours, and these ones are a manual download, unlike the other 2 data streams I've talked about. You can see a range of gases that are actually getting measured. The main focus we have is methane and CO2, but obviously we're keeping an eye on all the other data that comes through. Now, these results are heavily influenced by seasonal and diurnal processes. If we start by looking at the methane, you can see the methane in the bottom right-hand corner. There is very little evidence of methane. The spikes that came through, they all correlated very clearly to a time when either the gas clam was taken out of the ground or the batteries changed. So those data sets have been put aside as spurious data, and after a little bit more sort of review into them, and interpretation realized that we don't need to worry about those peaks. The volatile organic compounds, there was a slight increase that you could see in the period of around September 2024. And these were linked to a change in relative humidity. When we got the higher humidity, these peaks formed. It was monitored then in much greater detail. And through, again, the scientist who's involved in this, she was able to state that this is now normal and that is what was expected. The CO2 is a seasonal variation. It does really make sense. You get higher CO2 in the summer. This is because you have more plants, whereas in the winter, when you have fewer plants, the CO2 levels are lower. And you can start to see this variation also with slightly decreasing peaks, probably due to the fact that we are actually getting much more sustained and longevity now on the site, whereas initially there's quite a lot of movement around in the ground. So a bit of a summary of the gas clams. They were sort of medium cost. They're actually very high operational costs. You need to have filters, batteries, and there's an annual calibration cost. So reasonably high cost. You do need to do a manual monthly download and data QC. I do like to think of them a little bit of the diva of the sensor world, in that they are very susceptible to changes. They don't like changes in relative humidity. They don't really like changes in temperature, and they're not very keen if they get flooded. In fact, the one on site 5 often stops in the winter. So they are quite sensitive. However, they do provide a very good indication of any changes in the area, and we haven't actually identified anything that we can link directly to the operational. So my summary here is that we've got now approximately 5 to 6 years of baseline environmental monitoring data. This covers the pre-construction, the construction, and the post-construction stages. There's a lot of open data. It's available on our website. We can now use that data to provide a baseline, and therefore we now have confidence when we have deviations away from the baseline. It's also shown that many of these data sets are affected by their own diurnal and seasonal effects, and they need to be understood before leaping in and saying, there's a deviation. On the really plus side, through all this time, there have not been any observed notable changes to any of the environmental baseline monitoring parameters due to the operation of the geothermal infrastructure. Thank you.